All right, let's do this. So we got the notes. Okay. So I'm going to download the paper, then we'll get started. See. Okay, so I think that this is good. Let's just check the audio. So I think that this is good. Okay, I have confirmed that the audio is good. So let's get started. Cut. Okay, so today we're going to be reading a paper called Exaflow, a universal workflow system for exactly one stags. It's by folks from UC Berkeley, and folks from UC Berkeley and Anyscale, and folks from Anyscale. And Anyscale is a system that, or a company rather, that develops a system called Ray. And Ray, or that's at least one of their products. They work on an open source product called Ray. And I've previously written about Ray on my blog. And actually, before I get started, let's make sure to drop the link to the paper in the chat. So this is the paper we're reading. And it is for ExoFlow. So anyways, Ray is a system that is used for running distributed computation. In particular, it has, at least the last time that I learned about the system, it had this actor-based model, and in particular, Ray, I think, has evolved to train machine learning and AI models in a distributed way. And so I'm interested to learn about how ExoFlow connects to the existing work that Anyscale is doing. Also, folks from Anyscale went to go work at UC Berkeley. Folks from UC Berkeley went to go work at Anyscale. Ion Stoica is an author who, one of the paper's authors, who is very prolific, and so I'm interested to learn more. So on that, let's just, looks like, let's just check. Cool, got some viewers. So let's get started. I'm gonna do the first pass of the paper, and it takes about 15 minutes, or try to make it take around 15 minutes, and then we'll do a second pass where we go a bit deeper. On the first pass, I only read the introduction and then try to understand what the high level goals of the paper are. So on that note, let's get started. So given the fundamental trade-off between runtime and recovery performance, current distributed systems often build application-specific recovery strategies to minimize overhead. Okay, so right off the bat, they're talking about some trade-offs that systems make. So I imagine that they will talk about some improvement that they're making on how those trade-offs are made. Okay, so they're talking about how users must currently choose between building a single system which makes choices about these trade-offs for you, or combining multiple systems that don't let you, in order to get some configuration around the trade-offs. So my guess is that they are going to talk about how they've built a single system that lets you make these trade-offs. I also have read the abstract, so I don't really know anything about what this workflow system is, but just reading their one of the thing that you immediately pick up is, okay, this is the problem, and this is a potential area for improvement. So I really like that about the paper so far. Okay. So the key insight behind our solution is to decouple execution from recovery and provide exactly one semantics as a separate layer from execution. Okay, so there are different types of semantics for doing something. There's exactly once, which means that you have run the thing or received the message exactly one time. There's also at least once, which is, for example, in a message queuing system, the message will be received at least once, and if you process the same message again, then maybe the actual final output is the same because of a property called idempotence, where if you process the same thing, some unique key, an operation has a unique key. If you dedupe based on that unique key, then actually the operation, and you execute the same operation at the same time or multiple times, the output is the same. So there's at least once, and then they're talking about exactly once, there's at least once, and then there's at most once. So that means that there will, if the message exists, which is not guaranteed, or if the thing happens, which is not guaranteed, the most that it can ever happen is one time. So there are different semantics that you can offer with different levels of complexity to implement them. So that's what they're talking about. Exactly once semantics. Okay. So for generality, workflow tasks can return references that capture arbitrary intertask communication. Okay. Okay. So it says to enable the workflow system and therefore the end user to take control of recovery, we design task annotations that specify execution semantics such as non-determinism. So that is interesting because non-determinism means that you're not, if you execute the same function given the same data, you are not necessarily guaranteed to get the same result. For example, there are some sorting algorithms that are non-deterministic. If you give them the same data, they can actually maybe swap elements, for example. So being able to, or if you're running some computation, it could be helpful to say, actually, if you run this multiple times, you could get different results. And also, array, from what I remember. Let me just go to my blog where talk about array. I believe that they allow you to, there's tasks and actors that can execute the tasks, and I think you could, at the time, you could annotate tasks. You could annotate tasks. So here's my previous paper review. On array. So Exaflow generalizes recovery for existing workflow applications ranging from ETL pipelines to stateful serverless workflows while enabling further optimizations in task communication and recovery. Okay, so they're saying they have a general framework for solving this problem. It's not just for maybe actor-based systems. It could be for ETL pipelines or other things. And interested to learn what this means while enabling future optimizations in task communication and recovery. What are the further optimizations that it enables? So let's start taking some notes. Hopefully people can see this. Ooh, what's that? That's not what I wanted to do. Hopefully this is okay. Cool. So here we go. So what is this? So what is the research and why does it matter? Let's say that they have a generic workflow engine that allows users to, oh, that's what happened here. How do I close this? Close all? Okay, there we go. They have a generic workflow engine that allows users to configure the trade-offs, configure the system to make trade-offs between performance and recovery. Okay. So now let's get into the meat of the paper. Okay, so notes. So a key requirement for distributed applications is fault tolerance. Okay. Okay. So logging generally adds higher execution overhead but reduces recovery time. So an example would be that if you have a log of what the program does, it takes time to write that log to someplace, maybe disk or another persistent location. So that means that if the task crashes, or the thing that is running the computation crashes, then you can just go look at the log, and so you can pick up the task that is restarting, can pick up where it left off. So you have to say, well, we're going to write some things to the log, and that might take disk IO or something else, some other resources, CPU to write to the log. But maybe it's worth it in some situations. I could see how it'd be worth it for long-running tasks in particular. So they're also talking about checkpointing. Okay. Oh, cool. They're talking about different techniques. So Apache Spark and Apache Flink are two very cool open source technologies that support large scale processing. For example, if you want to run some distributed computation, Apache Spark is capable of doing that, whereas Apache Flink is more tailored towards stream processing. So as events come in, you're doing some processing and outputting some computation. And they talk about lineage-based logging and checkpointing. So I'd like to dig in a bit more on this in the future. Logging uses checkpointing. I'm familiar with checkpointing, and I'm not as familiar with lineage-based logging or the implementation details, but Apache Spark is open source, so I'm curious to see what papers they reference. It's been a while since I've written an Apache Spark job, so yeah, interested to revisit the technology. Okay. So they're saying if you get into some of the complications that users face. So they're saying that people combine streaming or batch with streaming. And so a machine learning pipeline might use batch ingest to build a training data set and then stream the data to a batch distributed training job. So, okay, so they're saying that you would use different recovery strategies for different parts of the pipeline. The other thing that's interesting about this is I'm not sure if this is all possible in Ray. Like, is Ray, what is the connection between what Anyscale does and this work? So I'm curious to hear more about that as we go on. I think Ian Stoica may also have been one of the authors of the original Spark paper, but let me check. Spark paper. Apache Spark paper. Is that correct? Yes, Ian Stoica was one of the original authors of the Apache Spark paper, along with folks like Matej Zaharia and Scott Schenker and Ellie Goodsey. I'm just looking at the article about Apache Spark that came out in, looks like 2016. So anyways, these frameworks are all related. I'm actually not sure if, did Apache Flink also come out of the Berkeley lab? Flink paper. I'm not sure. Apache Flink. It's an Apache project. Cool. Anyways, we'll come back to this. It's been a while since I touched these technologies because the company where I currently work I do not use them in my day job. So, interested to revisit them. But that is a side quest we can go on later. Okay, so Spark introduced continuous processing, but there are some shortcomings. It doesn't yet provide exactly once semantics during failures. Okay, so cool. So they had two different recovery systems in Flink. So basically building a recovery system that can handle both streaming and batch and has exactly once semantics during failures is difficult. So that's why it sounds like that's one of the things that is novel. I'm curious if they explain why you want exactly once semantics in the paper, but okay. So overall, these challenges have led to Apache support for applications that have diverse requirements in the recovery performance space. Users must choose between building on a single system and facing a fixed choice of performance. Okay, this is a restatement of what they said earlier. So I like the logic that they describe here, where they say, okay, you could build on a single system which has shortcomings. You could stitch together multiple systems that have has shortcomings as well. So that's what we're trying to solve. Okay. A workflow is a directed acyclic graph of tasks where each task encapsulates a function call and edges between tasks represent data dependencies. Okay. This seems familiar from Array. The Array paper. Let's see if I can pull it up. Let's see. If I pull it up. The Array paper. If I pull it up, you can see that. Do they talk about? Okay, so this is kind of what they talk about. There's application. Let's see if I can zoom in. There we go. There's application, and there are different tasks, and they return data that has some unique identifier. I guess you can't really see this, unfortunately, not very good. So we might have to come back to this, but it sounds like this idea of there's a graph. Everything is graph. Very common phrase. Many problems can be phrased as graph problems. So, anyways, this idea of a DAG seems related to Ray. I'm going to go back to the notes now. However, if you represent the problem as a DAG, something that Ray can do, I believe. And then there are relationships between tasks, which is the data, the tasks output. So the DAG API is popular because it allows arbitrary application code in each task, from submitting a Spark job to invoking a microservice. In contrast to other workflow systems, however, we decouple the unit of execution from the unit of recovery. Okay? In particular, Exaflow guarantees fault tolerance by durably logging the workflow DAG and coordinating task checkpoint and recovery, while execution of the DAG is handled by a generic backend. Okay? So they're saying basically that well, it's interesting because I feel like other workflow systems have tried to do this. I'm thinking of, there was a system called Airflow. There is a system called Airflow. Is it Apache Airflow? Which is for pipelines. And that is capable of running DAGs that have some generic backend. However, I believe that, so I'm curious, what makes Airflow different than this Exaflow? They also have both have flow in the name. So, yeah, what makes them different? What is the There's also another one called Dagster. Cloud native orchestration for data pipelines. So, e.g., so what's the relationship between Xflow and existing workflow systems? E.g., Dagster, Airflow, etc. So anyways, so separating recovery and task checkpoint has 3 key benefits. So first, it enables heterogeneous application pipelines that need multiple. So the DAG approach has several advantages. Oh, sorry, it's not the DAG approach, it's the decoupling execution from recovery has several advantages, which are run different recovery strategies, augment existing distributed execution frameworks. So they're okay. So I think that's one thing. This is a distributed execution framework, whereas I don't I wouldn't really put Airflow and Dagster in the distributed execution framework area. So they're exactly once. And then they actually mention Airflow. So that's very funny. So we'll get to that. So the third thing is it disaggregates the execution backend from recovery, allowing independent, so execution and recovery can be scaled independently, which is a nice property. One reason that it's nice to separate different concerns is that, well, it may be the execution takes 100 machines, but the recovery process doesn't take as much machines. So if you wanted to have recovery happen, or maybe there's some background backup process, who knows? By being able to scale them independently, you can allocate machines and really know what machines are doing, and you don't have resource contention necessarily. So anyways, that makes sense. Okay, so now we're going to talk about Airflow, which is funny because I was just talking about Airflow and I was wondering what the differences were. Okay, so for generality, workflow systems such as Airflow assume that each task is non-deterministic and may have side effects on external systems that in general cannot be rolled back. Okay. So this is actually example. Each task must checkpoint its outputs before they can be made visible to any downstream task. Okay, so this is a lost opportunity. Because it's a lost opportunity for performance because you can't parallelize. For example, large datasets passed between tasks can often be deterministically regenerated. Okay. So let's Okay, so oftentimes, so like you don't need to work with this assumption, is basically what the paper's saying. Let's see if I can make this bigger. Is there a way to make Obsidian bigger? Let's see, I'm a bit of an Obsidian noob. Oh, okay. That kind of works. There we go. Is that better? No, I think that's worse. Okay. Why am I futzing around with this? It was perfectly fine before. Okay. It was perfectly fine before. Why am I futzing around with this? Nobody was complaining. Cool. So, hello to the chat. Welcome. Looks like we have some folks who just joined. Please see the chat for the, paper that we're talking about. We're reading this paper called Exaflow. So please download it and feel free to follow along. Okay, so we're talking about what are the downsides of existing frameworks. And basically, the frameworks for running workflows don't operate with the correct assumptions, sometimes because and that correct assumptions with respect to, okay, we need to checkpoint data and we need to make sure that all the data is checkpointed before the next task can run in the workflow. So that's not always right, which means that performance isn't always very good. So in contrast, Exaflow, ... Okay. So instead of not knowing about what the application is doing, Exaflow gives control over recovery gives via some APIs, basically. Sounds like. First, we extend the typical workflow DAG API with pluggable first-class references to enable more flexible workflow internal communication. A workflow task can return references to its outputs, which the workflow system then passes to downstream tasks. In contrast, current workflow systems require the application to pass data by explicitly copying and checkpointing, which can be expensive for large data or implicitly through external storage, which makes it difficult to guarantee exactly what semantics. Okay. Okay, I'm a bit by using references. It sounds like the key idea is that Exaflow uses references to capture data movement in the relationship between tasks. So I want to know a bit more about what this actually means because it's a bit vague at this point. So, okay. So then there are two things that Exaflow does. And it allows annotations of a task. So that's interesting. Okay. Okay, during execution, Exaflow synchronizes the task execution and checkpointing. During recovery, Exaflow coordinates rollback, e.g. deletion of outputs from a previous execution. For example, before executing a task with an externally visible output, executing a task with any externally visible output, Exaflow will first synchronize upstream checkpoints to... Okay. So basically, Exaflow is built on Ray. There we go. So okay, so it sounds like the annotations allow you to do things effectively, and we will learn more about what Exaflow allows you to do. So Exaflow is built on Array and consists of a per workflow centralized controller. So we're going to learn about the infrastructure of Exaflow. Okay. 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 We show that references can enable 5x speedup for Spark data processing workflows compared to Apache workflow. Beldy. I have never heard of Beldy. So these optimizations are possible because correctness is ultimately guaranteed by Exaflow. These results also demonstrate Exaflow's universality. Okay, so now we get to the contributions, which are decoupling, execution from recovery, provides flexibility. This is what we're looking at. Provides flexibility. The workflow system provides exactly once DAG execution. And then they use Exaflow for a variety of applications. Cool. So that's great. Cool. So yeah. So we use exactly once semantics. Okay, so now we're going to go into the motivation. We'll come back to the rest of the paper later. So what's the API? The model. Okay. Guaranteeing exactly once execution. And then references. And then the architecture. Workflow execution. Workflow recovery. Execution backends. Implementation. ML training pipelines. Or sorry, this is evaluation. Okay, actually, sorry. Evaluation. And then let's see, stateless serverless workflows. Online, offline graph processing. And then micro benchmarks. Okay, related work. Okay. Okay. they're talking about a few workflow systems, data flow, actor systems, message passing systems, and then there's a discussion that we'll come back to, and then the conclusion, and then we'll review the references. Hello, welcome to the stream. Hopefully you can hear me. If you can't hear me, let me know. So what we're going to do is we're going to look at the conclusion, and then we are going to review the references, and then we'll take a short break. So okay, so many existing distributed systems provide specialized, efficient, and transparent recovery for specific application domains. Okay. However, when you want to have different types of applications, for example, streaming and batch applications, must have a general and interoperable recovery method. Okay, so they want to basically have one approach that allows you to, is easy to use and provides some functionality that is helpful, and that could solve the problem of you have different types of applications that are running or different types of things running in your pipeline, and you want to have recovery that is flexible for different types of things that you're doing. So that Exaflow is that solution. Okay, so they are talking about some of the, let's go to the references. Airflow XComs. Oh my gosh, I've used these. They're extremely painful. Airflow is another workflow system. You have Akka. You have some MLOps. They have Google Cloud Composer. TensorFlow. Interesting. I haven't read this paper. Got Delta Lake. Orleans. I've wanted to read this paper for a while. It's about a serverless framework. Interesting. Netherite, efficient execution of serverless workflows. Seems interesting. I've previously read a paper by some of these authors, in particular Konstantinos Kallas. I wrote a paper about distributed execution for kind of terminal workflows, and Konstantinos wrote a paper in that area. So that's familiar. A paper about Apache Flink. Okay. Kineograph. I am not familiar with this system. MapReduce. Okay. Oh, I've previously written about this from laptop to Lambda on my blog. So let's just mark that in blue. Falkirk Wheel. Rollback recovery for data flow systems. This is interesting. I believe Michael Zard, that name sounds familiar. Do you write Naiad or Dryad? Dryad, maybe that's why it sounds familiar. Dryad, yeah. Dryad distributed data parallel programs from sequential building blocks. So that's, yeah, seems to have been working in this space for a while. Okay. Dryad. Boki. This one this is from SOSP, Symposium on Operating Systems Principles 2021. It's one of my favorite. It's one of my favorite computer science conferences. It's coming up again this year. Ray, I've read that. Naiad, I haven't read this, but familiar, seen the name a few times. This one I believe is about, this is about Snowflake. Let's see. Okay. Ownership. Okay. This sounds familiar. I think I had this on my list of papers to read. Then you have RDDs, which is about Spark. Okay. Cool. So anyways, a lot of interesting papers that are referenced. I'm going to take a 5-minute break and then come back and read the rest of the paper. Okay, we are back. We are going to read the rest of the paper. I'm going to wait one minute. All right, so let's just start with motivation. I think we're going to go for about another 40 to 50 minutes. So here we go. We use exactly one semantics as our correctness condition. Okay. So more precisely, exactly one semantics require all outputs to appear consistent with a physical execution where all inputs were processed without failures. Okay. So they're talking about two factors: output visibility and determinism. Okay. 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 So let's just work through this. So you have a workflow DAG, and so for an internal thing that is internal task that is non-deterministic, you're going to the way to recover is to commit the output, or on failure you make the data not visible anymore. And then for an external non-deterministic computation, we commit the output before visibility, or if possible, roll back visibility on failure. Okay, so basically what they're saying is that for non-deterministic computation, you want to commit the output or be able to roll back the fact that that output could be used, both for internal and externally visible computation. So I think that that's rewording what they said here. It's a bit confusing, but looking at the figure here, I think I understand. So, and the reason that you need to think about this is because if you have some computation that you're doing and you're basing other computation on the previous computation, and the previous computation is non-deterministic, then whatever you're doing later could change. I think that that's the simplest way of LLMing what the paper is saying. Okay, so handling non-deterministic outputs. Handling non-deterministic outputs is generally done in two ways: global checkpointing and rollback on failure, or logging and deterministic replay on failure. Okay, so there are two approaches. And then non-deterministic outputs are handled by global checkpointing and rollback, and then logging and deterministic replay. And this is basically committing what's already been done, so that if there's any non-determinism, you can still redo the execution from a point to try to lessen the impact of the non-determinism, or reduce it, or stop it. For outputs that cannot be rolled back, however, upstream non-deterministic outputs must first be committed by taking a global checkpoint. So basically, the point that they're making is that if you're doing something that's not deterministic, you need to commit the data, or you need to commit the outputs or in progress things. Whereas for deterministic computation, if you know it's deterministic, then it makes your life a lot easier. So, yes. So there's this cost that you incur for non-determinism. So current workflow systems guarantee exactly what semantics by durably checkpointing each internal output before making it visible, and requiring the developer to make external outputs idempotent and durable. Okay. The key insight behind Exaflow is that knowing the DAG structure makes it simple to identify a consistent execution frontier, allowing the recovery methods before and after the frontier to be decoupled. For example, A out is internal to the outlined subdag in figure 1a. Okay? And thus its recovery method can be chosen flexibly as long as the inputs and outputs are consistent. Okay. So thus, our solution consists of two parts. First, references enable Exaflow to capture a broader range of intertask communication as internal outputs. Okay. 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 So basically, references enable Exaflow to capture a broader range of intertask communications as internal outputs. Okay. Without being involved in the physical communication. Okay, let's come back to this and see what else they tell us. We use 3 representative applications to show the value of making workflow internal outputs more flexible, and 2, exposing application semantics to the workflow controller. Okay, so you have some ETL pipelines, you have ML pipeline, and then you have some serverless workflows. Okay. Okay, figure 2a shows an example in which a Spark job A performs batch data cleaning and writes the data to an external database. Okay. Okay. Okay, so they're talking about a problem with airflow, for example. So here is the example problem. You have a job that does some computation and writes the computation someplace, and then B and C both read that data from the initial computation. However, the problem is that there is a bunch of, ideally, you wouldn't have to write and then reload the data and write the data in one job and then reload it in the following jobs. Ideally, you could write it to memory and then B and C would just read directly from memory. So there's that. Then you have, so ETL pipelines, basically the jobs have to reload the data in between steps, which is not good. ML pipelines are similar, but with an ML application as the end consumer. Okay, so you have 2C. So you have, shows a typical ML training workflow. Training data is extracted and transformed in the ingest task and then consumed by a distributed training job. Okay. Okay, so basically, ideally, the ingest, so basically the key insight is that currently, if you want to do some more complex computation, you need to potentially reload the memory across the different jobs. So you write the data and then you read the data later through a different step. But what if you just had one job that handled the ingestion, augmentation of the data, and training on the data in one, and also serving as well? Yes, so they can't effectively orchestrate. So I think this is actually only training. Does it actually talk about? Doesn't talk about serving, but still, the training of the model requires a bunch of reading and writing to disk, which is wasteful and bad for performance. Okay, so then we have so then the note on this is having to perform data in different steps, perform operations I think this is really where Ray comes in, because Ray is theoretically capable of building this, and Ray is open source, even though Anyscale is productionizing it and making an enterprise version available. It's open source. So anyways, Ray, you could say, well, there's an operation that loads the data in, and it is in this actor, and then the output of this actor can be consumed by some training task later. So that's the background, because this looks like something that you would write in Ray, like a distributed execution in Ray. Okay. Cool. So then we have serverless workflows. Okay. Okay. Each system implements their own recovery procedures. Okay. So basically there are frameworks for running distributed serverless applications. However, they also have their own recovery mechanisms, basically. They're custom. So Exiflow theoretically replaces some of this. I guess we'll learn more. Okay, so what's the API? So Exiflow is a general workflow abstraction workflow layer that abstracts a workflow backend. Okay. Okay. Okay, so there's API here. There's a DAG interface. Table 1. So the application invokes workflow tasks and specifies arguments using f.bind. The caller receives a workflow DAG that represents the task output and that can be passed to other tasks as dependencies. Workflow execution is lazy. To evaluate a workflow DAG, the developer must run it. Cool. So there's like some static checking of the workflow. Okay. Okay. So then there are task annotations. So there's a way of setting up the DAG, annotating the tasks, and what else? The application specifies whether to skip checkpointing a task's output. The workflow system guarantees correctness, so this can be considered an optimization hint. Okay. Yeah, I mean, this sounds interesting. I'm curious how much the developer actually has to do, because it would be great because how do you know, I guess, if your task actually is deterministic? That seems like a thing. Ideally, this could be figured out automatically by your by a system that you're using, so you didn't have to do as much thinking. But maybe that's not possible. Okay. The application specifies whether a task can be rolled back, and if yes, how to do so. Okay. Cool. Okay, this is very cool. So direct task outputs are subject to limits of the execution backend. Okay. Okay, so then there's a ref. Refs allow execution backends to store data, to store outputs. Then, upon failure, Exaflow can either restore the ref from a checkpoint or trace the DAG back to the creating task. Okay. Okay, I'm interested to hear more about these actor refs. Okay, there is some... let's see. Okay, there's some mathematical formulation. I'm probably going to skip this actually. Or I will review it at a later time. Okay, so again, they have some invariants about when you can roll back tasks and rollbacks. So that's interesting. I'll come back to it. Okay. Okay, so for example, figure 4b shows how, where's 4b? For example, figure 4b shows how the ingest task from figure 2d can use refs to return distributed in-memory data. Okay. So passing references, small boxes in an ML workflow. Blue refs are actors that wrap TensorFlow worker state, passing an actor ref and an ETF workflow. Okay. Okay. I see. So basically, this is under the references section. So, okay, basically there are locks on refs that could, or there are constraints rather, on refs that could change. Like you can't write to a ref that, you can't write to a ref that is being read by another task. And that simplifies recovery. Okay, so let's now learn about how this works with Ray. Workflow controller. Okay, so now it's so we have the to-do figure 5. Okay. The execution backend should implement a remote function invocation interface. The backend should provide the ability to detect and report task and ref failures, and 2, guarantee no resource leaks for failed task executions and refs. Okay? The controller runs as an event loop with the following events: task or checkpoint completes, and task or checkpoint fails. Okay, so workflow execution. So they have the workflow control layer. Okay, so thus Ray task and actors is a string from workflow tasks and actors, which execute exactly once and can be natively checkpointed. We use Ray actors to implement the workflow controller and task executors. The controller uses Ray's distributed features to coordinate task execution and checkpointing. So reference to Ray and distributed features paper, which the distributed features paper was written by some of the same authors. Okay. 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 So it's a state machine. On run, the controller logs the workflow, DAG specification, arguments, ops, etc. to durable storage and triggers execution. On each iteration of the event loop, the controller may select a workflow task whose inputs are ready and submit the task to an executor. Okay. Okay, cool. So basically, when the workflow knows that there is something that is ready to be, so let's read this. Okay, so the ID is C, the argument is A. It's waiting on the output of it is 1BF, And so that means that D is waiting on C and B. Okay, so there's some relation. It's a graph. It's a graph. Amazing. It's a graph. So checkpointing is carried out asynchronously by background threads on the executors, enabling parallel and distributed checkpoints that are not bottlenecked by the centralized controller. So, okay, so there's some background checkpointing, and there's some synchronization the controller monitors the checkpoint being done. And it talks about situations in which the synchronization of the state of the checkpoint is required. Okay. Exaflow handles passing and checkpointing application references. When a task finishes, the executor replaces any refs and actrefs appearing in the task's output with placeholders, e.g. X in figure 5. Okay, hold on, let's read. Handles passing and checkpointing application references. In the task. Okay. Okay. So workflow recovery. The controller handles task and checkpoint failures. Task frontier. That's come up again. So I suppose because we lost A's cached output. Then we walk the DAG backwards from C and add each visited task node to the re-execution set. For each task, we check argument availability, i.e. whether the value has a checkpoint or a live ref. Else, we add the tasks that create, so basically you just walk the graph backwards. Graph algorithms, amazing. The visited task has deterministic equals false, then we also add all tasks downstream to the re-execution set. Cool. Thus, if C fails and we need to re-execute A, we also re-execute B. Okay, so, okay, that makes sense. So in this case, B is, or A is non-deterministic. So if we need to re-execute A, then we also need to re-execute B. Is that what that says? Yeah. Okay, that makes sense. From the re-execution task set, we carry out rollback. In reverse topological order of the re-execution set, we first clear any cached output refs. Okay, so basically, if things are non-determined, it's very cool. Like, it's just a graph algorithm that you run, and you figure out what needs to be rerun based on some conditions. So, So they're talking about the correctness. I believe them. Execution backends. So execution backends. Exaflow references are compatible with existing third-party mechanisms for task communication and recovery. Okay, so basically there are Exaflow integrates with backends, and the backends could use these annotations. I'm curious, actually, is Exaflow open source? I don't know. Okay. So the implementation is actually fairly small. Exaflow is built on Array v2.1, which uses gRPC. Okay. Okay, so to build Exaflow on another actor system such as Akka or Orleans, you must implement refs. So they reference other actor, oh sorry, this is actually implementation. They reference other actor systems that they could use, but they reference other actor systems that they could use, but they would have refs on. Okay, so interesting. Okay, so now the evaluation. I always like how folks lay out, lay this out. So main questions to answer. Okay, so then they have some baselines, standard mode, okay, express mode, okay. Okay. So we show how, okay, so we show how Exaflow enables a flexible recovery performance trade-offs for the workflow in Figure 2D. Okay. Okay, cool. Okay, cool. So basically, they have different options for checkpointing. different options for checkpointing can impact performance. And you got sync checkpoint, no checkpoint, and you got async checkpoint. All right, and then, okay. Okay, so end-to-end duration for the ML workflow application shown in figures 2D and 4B. End-to-end duration without failure. Right, end-to-end duration with different failure types. Okay, and there are multiple steps. You can see that if you are doing, as the data set grows, if you're doing synchronous checkpoints, the time goes up predictably. Then, if you look at different failure types and compare what the failure types look like, if you compare the how different checkpointing schemes work with different failure types, then you can see changes in execution time, theoretically, I guess. Let's keep reading. Okay. Okay. Cool. Okay, so basically, this is very cool. So, this is cool. So then they're basically saying that figure 6, let's copy this. Different options. So the cool thing is that they can say that in normal conditions, checkpointing impacts performance. So, however, if you look at the failure conditions, the differences between different checkpoint approaches and performance and time to execute gets smaller. Okay, that makes sense. So basically, they are forcing the, under situations where the cluster goes away, the differences between the synchronous checkpoint and the asynchronous checkpoint and the selective asynchronous checkpoint all they get smaller. And you can see it makes sense that relatedly, in normal conditions, synchronously checkpointing all the time would be bad for performance. Okay? So this demonstrates that it can recover from failure, I guess. So we compare ExaFlow on a travel reservation benchmark. Okay, so this is showing that there are differences. The summary is there. Exaflow is better than the existing frameworks for running serverless functions, stateful. That's what it theoretically shows. Okay, online, offline graph processing. Distributed graph processing can be generally divided to stream versus batch processing. Streaming systems can handle continuous updates and produce timely results, but may not offer the same precision as batch systems. Okay. Okay, so what is this? This is, where is this? Graph, figure 7C. So basically the latency of tweets being available, or posts, I guess now, on x.com, whatever they're called now, the latency is lower with different checkpointing systems when implementing a graph processing algorithm. Different checkpointing approaches. Okay, then what else is there? Micro benchmarks. With equivalent backends, Exaflow matches or reduces execution overheads of existing workflow systems. So, okay, so they're making some claims about just on very basic things. That's what the micro benchmarks are generally about. So they're basically saying that for the same backends, you can get better, for the same backends, Exaflow can get better or the same performance with some added benefits. Okay. 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 Great. Better on latency. data sharing for ETO. Okay, so then data sharing, it can do that. It can do it. Do it and you can see. You can see when compared to Spark jobs that don't share memory. And then okay, so if you want to, so they're saying Exaflow itself, maximum task throughput, 1 task per day. So how much overhead does Exaflow actually add? Exaflow, Wait, the number of controllers to have 15,000. Okay. So the number of controllers, what is this saying? Okay. So on one node, this is kind of hard for me to read because I am colorblind. So it looks like they basically, okay, so on one node, they kind of max out at the same thing. And then there's some overhead for what is this saying? Okay. Okay. So this is basically, there are some challenges with Exaflow. Exaflow overhead. That's what I read. It adds some overhead to run the workflows. I wonder how big of a problem that overhead would actually be. That's it for the paper. That's all I'm going to read tonight. So on that note, stay tuned for a future paper review on my blog. And until next time.